Hello everyone. In this lecture we look at one of the most important aspects of this work, power and energy topic, which is the work energy theorem. In fact, to put it in a very simple term, the entire topic of work, power, energy will be revolving around this one idea of work energy theorem. So what is this work energy theorem? We'll be able to take a look at it in the next couple of minutes. Now when we talk about energy, generally we keep hearing various types of energy, like we talk about kinetic energy, we talk about potential energy in case of gravitation, in case of spring, in case of the charges which we call as electrostatic potential energy, and we talk about chemical energy, which is the energy stored in the objects, the chemical substances. We talk about the electrical energy, which is one of the most useful form of energy for us. In fact, the systems that we use, or the electrical equipment that will be operating, everything will be running based on this electrical energy. We have magnetic energy, we have sound energy, we have light energy. Light energy is the form of energy which we get from the luminous objects. We have heat energy, which is also called as thermal energy. So this is supposed to be the energy stored in the objects due to the temperature. So a body at high temperature is supposed to have high amount of heat energy, and a body at low temperature is supposed to have less amount of heat energy. And we have nuclear energy, which is also an abundant source of energy. And when we talk about various types of energies, it will be interesting to understand how each of these energy is getting stored within the object. Now we'll go and take a look at this kinetic energy, and we see that most of the forms of the energy that we are discussing over here are nothing but in one way or other related to this kinetic energy. So it will not be exaggerating to say that kinetic energy will be the only real form of energy that an object can possess. Now we'll try to understand what do we mean by this as we go along this lecture. But to talk about what is the kinetic energy, it is the energy possessed by a body by the virtue of its motion. And this is what we call as kinetic energy. Flowing water, it's moving, so it will have kinetic energy, and we can use it to run the water mills. And moving vehicles, they possess kinetic energy. Moving air or wind, it possesses kinetic energy, which is used to run the windmills, and even it is used to run the wind power plants. And if we are moving a hammer to hit an object, then it will have kinetic energy, and this will be used to drive the nails in the wood when we hit a hammer basically onto a nail. And a bullet fired from the gun will also have kinetic energy, and due to this it will be able to penetrate into any target which we are trying to hit with the bullet. So kinetic energy is basically the energy that an object will have by the virtue of its motion. Now when we say that the kinetic energy is the only real form of energy, if you look at some of the other types of energy that we discussed, let's say we talk about thermal energy. So thermal energy is what we are referring to as the energy possessed by the body because of the temperature. So if you look at what this thermal energy essentially is, when we look at the matter at a micro level, so we have the matter made up of atoms or molecules, and these molecules in case of a gas will be in constant motion, where they can go and occupy the entire volume of the container. And in case of a liquid, they will be able to move freely within the volume of the liquid. And in case of the solid, what we see is these particles will be under constant agitation, or we can call them as vibrations. Now the total sum of all these micro level energies, so when we talk about the micro level energies, we are essentially referring to the kinetic energies of various form, whether it is the kinetic energy because of the velocity, linear motion of the object, or kinetic energy because of the vibrations. And later in the rotational motion topic, we will try to understand what will be the kinetic energy in case of rotation. So these various types of kinetic energies that are associated with the micro level particles, when we sum it up, that is what we are referring to as the thermal energy. As we increase the temperature, the thermal agitations, the thermal motion will also increase, and thereby the thermal energy will be increasing. And if we reduce the temperature, the thermal agitations and thermal motion will reduce, and thereby the thermal energy also will be reduced. So kinetic energy in that sense is one of the real forms of energy that a body can possess. Now we'll take a look at how we'll measure what is the amount of kinetic energy possessed by a body. So we know that a moving body will have kinetic energy, a body at rest will not have kinetic energy. So we'll try to see what is the amount of kinetic energy that a body can possess. To arrive at this expression, we'll look at two cases. One where we can do the derivation using the simple equations of motion that we are aware of. This we will be able to use when there is a constant force which is able to give rise to a constant acceleration. So let us say we have a body of mass m which is starting with initial velocity 0, and there is a constant force F acting on it, which means that will be able to produce a constant acceleration a. So we'll have the relation F is equal to m into a, or a is equal to F by m. Now we look at a case where the object is traveling through distance s. Since it is moving along a straight line, the case that we are assuming here, the distance covered and displacement both will be same in terms of the value, and the object let us say is reaching to a final velocity v. Now we'll try and see how we can calculate the kinetic energy possessed by the body. So of course, initially, since the object is at rest, it's supposed to have no kinetic energy or kinetic energy 0, and when it is picking up the velocity, it will be able to have kinetic energy. So if you look at the relation between the parameters of motion, we have since the assumption is that we are dealing with a constant force over here which is giving us constant acceleration, so we can have v square is equal to u square plus 2as, where the final velocity square is equal to initial velocity square plus 2as, and we know that the initial velocity here is 0. So if you substitute the value of initial velocity to be 0, we'll get v square is equal to 2as. From here we'll have the displacement value, which is also equal to the distance covered, will be equal to v square by 2a. Now when we want to find out the work done by a constant force, so we already have the expression F into S into cos theta, where theta represents the angle between the force and the displacement. In this case, the assumption is that the only force acting is creating the displacement, so both of them will be in the same direction. So work done by this constant force will be equal to simply F into S, which will be force will be the mass times of acceleration into the displacement. So we have m into a into displacement value just now we have found in terms of the other parameters will be v square by 2a. So a will be cancelled. So what we have is half mv square. Now this is the work done by the constant force in moving it from the initial state of rest to the final state of velocity v. This work is getting stored in the form of kinetic energy of the object. So the kinetic energy of the object which is moving with a velocity v will be half mv square. Of course, we have done the derivation under the assumption that we are having a constant force which is able to provide a constant acceleration. Now we can do the derivation even for a variable force by using the calculus method. Let us say we have a body which is initially at rest, and we are applying a force. The force may be a constant force, force may even be a variable force on the body to displace it along the direction of the force. Since we are talking about only one force being applied, the displacement will be in the same direction of the force. So what we can look at here is we have an object and there is a force acting on it, So we are not going to consider that the force is a constant force. Force may be even variable. Let us say the mass of the body is m, and initially it is starting from rest, so it is going to go on, and finally let us say it is reaching a state where the velocity v is v. Now as we look at the force being also a variable force, we will not be able to use the work done for a constant force. So we will have to be using the work done by a variable force. So if you look at some intermediate position, let us say the velocity of the object is u, and we give a very small displacement further ds. Of course, this displacement will be in the same direction as the force. Now for the small displacement that we are creating, the work done will be equal to F into ds. Of course, F will be mass times acceleration into ds, and acceleration we can write it as the rate of change of velocity at that time. We have a property of the differentiation, which is m into, I can write it as du into ds by dt, by just shifting the dt from here to the other denominator. The ds by dt is nothing but a rate of change of displacement, which is the velocity at that instant u. So which will have m into du into u. We can just move the terms and have mu du. So this is the small work done for the differentially small displacement that we are creating. Now if we want to estimate what is the overall work done by the force, we must integrate it in such a way that the velocity value is changing from the initial 0 to the final v. So the term which we are going to integrate is mu du, and since m is a constant, it can come out of the integration, and we'll have integral 0 to v u du. This is basically like integral x dx, which is equal to x square by 2. Of course, we have to substitute the limits. So what we'll have is m into u square by 2. The limits are 0 to v, which means it will be equal to m into v square by 2 minus 0 square by 2, which will give us the final value half m v square. So this work is getting stored as the kinetic energy in the object, and thereby the kinetic energy expression will be half m into the v square. So this is the amount of kinetic energy that a body will be having. And since we're talking about the kinetic energy expressed in terms of the mass of the object and the velocity, so under the assumption that we are going with a constant mass, the velocity will depend upon the frame of reference, which means if we look at the object from different frames of reference, the kinetic energy value might be changing. For instance, we look at the kinetic energy of a person of mass m sitting in a train moving with a speed v, which means along with the train the person also will be moving with a speed v. If you look at what is the kinetic energy in the frame of train with respect to say somebody else who is also sitting in the train, this person will appear as if he is at rest, so the kinetic energy value will be 0. Whereas if you see from somebody who is standing outside from the frame of reference of the earth, we'll see that this person of mass m is traveling with a speed v, thereby the kinetic energy value will be half mv square. So kinetic energy does depend upon the frame of reference, and we already discussed previously that work also depends upon the frame of reference. Now we come to the important aspect of work energy theorem. So work energy theorem basically relates the work done on an object to the change in kinetic energy of the object. So when we look at an object of mass m, and if we are doing a very small work dw, this will cause a change in its velocity or speed. And in the derivation for the kinetic energy, of the calculus method, we have seen that the dW value will be equal to mu du. The small work done in causing a very small displacement will be F into ds, and F will be m into a into the ds. A will be du by dt into the ds. So on taking the dt to the other part, we'll have m du into ds by dt. The ds by dt is nothing but rate of change of displacement, which is the velocity. So m du into u, which we are writing it as mu du. So if we look at an object which is moving, and the small work done by a force, the force may be a constant force or a variable force, will be equal to mu du. So if you want to find out what is the overall work done by the force, we'll have to integrate this expression where let us say the initial velocity of the object is vi and final velocity of the object is vf. So we'll integrate the term mu du between the limits initial velocity to the final velocity. M is a constant, it will come out of the integration. So what we have, integral v initial to v final u du. Now this is like integral x dx, whose value will be equal to x square by 2. So m into, we'll have to x square by 2, or I can write as u square by 2. The limits of integration are v initial to v final, which means m into v final square by 2 minus v initial square by 2. This is nothing but, if we expand it, half m into v final square minus half m into v initial square. This is nothing but the final kinetic energy minus initial kinetic energy. So if you look at work done on an object, then the work done on the object is equal to the final kinetic energy value minus initial kinetic energy. So we can put it as work done on an object will be equal to change in kinetic energy of the object. Now this is what we call as the work energy theorem, and work energy theorem basically states that work done by a force acting on the object will be equal to change in kinetic energy of the object. Now this theorem is valid for all type of forces, whether we talk about the conservative forces or non-conservative forces, external, internal. So here when we talk about work, the work may be done by multiple forces. Since work is a scalar quantity, so if many forces are acting on the object, then work done by the first force plus work done by second force and so on, the total work done by all the forces will be equal to change in the kinetic energy, which we can represent it as delta Ke. So delta refers to change in the value of the kinetic energy. So this is what we call as work energy theorem. Now the kinetic energy of the body will be increasing if we are doing a positive work on the object, and this would be happening when the force applied is able to create a displacement which is in the same direction, which means the body is moving in the direction of the force. And the kinetic energy will be decreasing when we are doing negative work. So that will happen when the object is moving in the opposite direction to the force. So we look at examples of that. If we consider vertical motion of a body under the influence of gravity, now when we are projecting the body upwards, what we see is the body is moving in opposite direction to gravity. So since gravity will be always downwards, so in this case work done by the gravity will be negative. So we see that as the object is going up, the kinetic energy of the body will keep on decreasing. Whereas if you consider an object which is falling down under the influence of gravity, here the displacement and the gravity will be in the same direction. So work done by the gravity will be positive. So the kinetic energy of the object which is falling down will be keep on increasing. Now when we take a body which is moving on a rough horizontal surface, so we'll have friction. So if you have a body which is moving on a rough horizontal surface, let us say the body is moving towards the right side, then the frictional force will be towards the left side. It will be always opposing the relative motion between the two surfaces. And here we will see that work done by the friction force will be negative. So since friction is doing negative work, we will see that the kinetic energy of the object will be keep on decreasing. So these are some of the aspects with regard to the work energy theorem. Now we'll see a couple of sample problems on the applications of this work energy theorem. Let us say we have a body of mass 20 kg whose initial velocity is 6 meters per second. The question is, we need to find how much work should be done in order to increase its velocity to 10 meters per second. So this is a straight question on the application of the work energy theorem, where we have work done on an object is equal to the change in kinetic energy, which means it will be equal to Ke final minus Ke initial. So here mass of the object is given as 20 kg, and initial velocity, let me represent it as u, is 6 meters per second. Final velocity, we'll represent it as v, is 10 meters per second. So Ke final will be half into, so we are not going to use the units over here because already all the quantities are in the SI system, and we know if all of them are in the SI system, the work will be coming in joules. Half into 20 into the final velocity is 10, so it will be 10 square, minus half into 20 into the 6 square, so which will be 2 ones are 2 tens. Already 10 square is 100, so 100 into 10 it will be 1000, minus here we will have 10 minus 360, it will be equal to 640 joules. So work done that is required to increase the velocity from 6 meters per second to 10 meters per second will be 640 joules. Now the work energy theorem is also useful in doing some calculations like stopping distance. Now what we mean to say by the stopping distance is, let us say we have an object which is moving like a car, which has a velocity v, and in order to stop it, we must apply a retarding force, maybe friction or any of the other retarding forces, which will be in opposite direction to the direction of motion. And when we talk about the case of stopping, final velocity must become 0. Let us say the object is moving through displacement x before it stops. Now we can find what is the stopping distance by using the work energy theorem. Let us say here the retarding force is a constant force which will be in opposite direction to the displacement, so which means the angle between them will be 180 degrees. Now work done by this retarding force basically will be F into x into cos 180, means it will be equal to minus F into x. Here F is representing the retarding force, it may be a friction force. Now the change in kinetic energy of the object, assuming that the object is having a mass m, will be half m into the final velocity will be 0, because finally it is coming to the rest or the stopping state, minus initial kinetic energy will be half into m into the v square. So this is totally 0, so the change in kinetic energy will be minus half mv square. Now work energy theorem basically states that work done on the object will be equal to change in its kinetic energy, which means minus F into x will be equal to minus half mv square. Minus minus will get cancelled. So what we have is x, which is the stopping distance, is equal to mv square by 2f, where here m represents the mass of the object, v represents the initial velocity of the object before the retarding force is applied, and f basically represents the retarding force. So this is about the stopping distance of an moving object. We can even look at an illustration based on this. Let us say we have an object of mass 200 kg which is moving with an initial velocity of 10 meters per second on a rough horizontal road, means there will be friction on this road. If the coefficient of friction between the object and surface is 0.2, now they are not mentioning what is the coefficient of friction. Since we already have a case which is the motion between the two surfaces, we assume that this represents the kinetic friction coefficient. We need to find what is the stopping distance, and also the value of g, we can take it as 10 meter per second square. So we look at the situation over here. As we can see, we have an object of mass 200 kg which is moving with an initial velocity of 10 meters per second on a rough horizontal surface. Now the object is moving only in the horizontal direction, so along the vertical line there is no motion. So why we are looking at the vertical line is, as the object is moving towards, here in this case we assume it to be the right side, the frictional force acting on this will be towards the left side, and kinetic friction will be equal to coefficient of kinetic friction into the normal reaction between the two surfaces. So if you look at the vertical line, so we'll have a normal reaction acting which is vertically upwards, and weight of the object. So weight of the object will be m into g. Mass is 200 kg into g, we can take it as 10 meters per second square, so totally it will be 2000 newtons. This is the weight of the body. Since along the vertical line there is no motion, it will imply that vertical line there will be an equilibrium of forces, means normal reaction will be equal to weight. So thereby the normal reaction value will be equal to 2000 newtons, and hence the kinetic friction value will be equal to mu k times the normal reaction, which will be equal to 0.2 into 2000 newtons, which will be equal to 400 newtons. This is the kinetic friction value. Now this is the retarding force acting on the object. Now we can straight away use the formula that we have just derived, which is stopping distance x will be equal to m into v square by 2 into f. Otherwise we can even do the derivation all over again, but since we just now concluded the result, we can use the stopping distance formula. Here of course the friction force which is causing the retardation is a constant force, because as the object is moving and till it comes to rest, the final state is the 200 kg object is having a final velocity which will be equal to 0. So the stopping distance value will be m, which is 200 kg into v square. The initial velocity before the motion is starting is 10 meters per second whole square by 2 into the retarding force, which is 400 Newton. Of course we can do away with the unit because all of them are in the SI system. So what we have is 200 into 10 square will be again 100 divided by 2 into 400. So 200 ones, 200 twos, 100 by 4, which will be equal to 25, and the unit is going to be meter. So in this case the stopping distance value before the 200 kg object comes to rest will be 25 meters. Now this is about the application of work energy theorem. Now kinetic energy is one of the properties of an object which is in motion, and same is the case of linear momentum, because if an object is in motion, we have a property called as a linear momentum, which is a vector by the way, which is measured as mass times the velocity of the object, whereas the kinetic energy object is a scalar, it is not a vector, which is measured as half m into v square. Now in vector form we can represent this as half m into v dot v, because the dot product of a vector with itself will be equal to square of the magnitude of the vector. So we'll try and look at what is the relation between the kinetic energy and the linear momentum. Of course here we'll just look at what is the magnitude of the linear momentum. So magnitude of the linear momentum will be m into v. Now when we square it, it will be equal to m square v square. We'll just take one m out, and what we'll be having is mv square. So this mv square, because kinetic energy is half mv square, if we take the 2 from here to the other side, we'll have mv square is equal to 2 times the kinetic energy. So we can have it as 2 times the kinetic energy, which is p square. So thereby what we have is p square. If we bring the m as well as 2 to the other side, p square by 2m is equal to kinetic energy. This is one relation, or we can also write it as P will be equal to root of 2 times mass of the object times its kinetic energy. So these are the two relations between the linear momentum and kinetic energy of the object.